Okay, so today we're going to talk about trigonometry and complex numbers, which is a very interesting subject, I think. It is very useful. So here's the terminology we're going to use. So a triangle means trójkąt, quadrilateral means czworokąt, angle means kąt, acute angle means kąt ostry, right angle means kąt prosty, obtuse angle means kąt rozwarty, hypotenuse is przeciwprostokątna, opposite is przyprostokątna przeciwległa do kąta ostrego, adjacent is przyprostokątna przyległa do kąta ostrego, imaginary number is liczba urojona, complex number is liczba zespolona, unit circle is okrąg jednostkowy. So here are the definitions of the 6 trigonometric functions. You can basically forget about these two, secant and cosecant. They're not really used that much, but these 4 are pretty useful to know. So in a right angled triangle, for an angle alpha, the sine of alpha is the ratio of the opposite to the hypotenuse. The cosine of alpha is the ratio of the adjacent to the hypotenuse. Tangent is the opposite to the adjacent, and cotangent is the adjacent to the opposite.
Okay, so here we may see unit circle, which lets us see as trigonometric functions in different way. Here is circle with radius 1, and sinus alpha is opposite by hypotenuse, and because hypotenuse is just 1, it's radius of this circle. So sinus alpha will be just opposite, which is this red line, this shorter red line, which you may easily see. The cosinus alpha is adjacent by hypotenuse, and here again hypotenuse is just 1. So cosine alpha is just adjacent, which is the green line, which you may also easily see. Then the tangent alpha, tangent alpha is opposite by adjacent, and here opposite is also the radius of this circle. And so the tangent alpha will be just opposite.
I think the adjacent is the radius here. It's the adjacent, and here's the opposite.
The adjacent is radius. So tangent alpha will be just opposite, which is the longer red line, which you may also easily see. The cotangent alpha is adjacent by opposite, and opposite is here just 1. So cotangent alpha will be just adjacent. Yeah, so it's the green line.
So when we're talking about angles, any angle, we have 2 main options of measuring them. We can divide the circle into 360 equal parts, which we call degrees. So a full rotation is 360 degrees, half a rotation is 180 degrees, a quarter is 90 degrees. I'm sure you're familiar with this method. And the other option is to define an arc on a circle, its length is equal to the circle's radius. The angle that this arc makes is 1 radian. So a full rotation is 2 pi, half a rotation is a pi, and quarter rotation is pi over 2. So, for example, 30 degrees would be pi over 6.
So here we may see some important trigonometric identifiers. So the first one is really useful, and it's used in many proofs. Then the last four ones let us broaden the trigonometry sinus and sine and cosine functions to each cont, not only to a butte angle. So, and what is also important, sine and cosine are periodic functions, and period is 2 pi.
So let's now talk about imaginary and complex numbers. So let I be a number such that I squared is equal to -1. We shall call it the imaginary unit. And as you probably noticed, this number isn't on the number line. That's because there are only real numbers on the number line. To see the complex numbers, you need to get out of the real number set. These numbers can be expressed in the form a plus b times I, where a and b are real numbers and I is the imaginary unit.
Okay, so here we may see adding complex numbers. It's the complex plane, and what is quite interesting, adding complex numbers is like adding vectors, and we add just a real number to real number, and amount of e number, and to amount of to another amount of e number. So as we may see here, a plus be plus c plus de is just a plus c plus a plus b and d. So the 5 minus e is just sum of 3 and 2e and 2 minus 3e. And if we added like this these vectors 2 minus 3i and 3 plus 2i, we would in triangle method of adding vectors, we would the result of it would be the place where is 5 minus I.
So let's now talk about complex multiplication. So let's just look at this complex plane we have here. We have a number z, which is equal to 2 plus I, but that's not really important in this example. 1 plus z, 1 times z would be still z, so you may think of it as 1 moving over to the point z here. 2 times z would be 4 plus 2i, which you may think as 2 moving over to this point. I times z is interesting, because it, as you may see here, algebraically, makes it -1 plus 2i, which is basically rotating the number z 90 degrees around the origin of the unit circle, of the complex plane. And multiplying the number z times g gives you the number 5, because the imaginary parts cancel out. Multiplying two complex numbers is basically like multiplying two sums. You multiply every part of the parentheses with every other part. Oh, and here you have also the multiplication of I times z by I, which again rotates it by 90 degrees, which, as you can see, makes it so that this I squared times z is just the opposite of z, the 180 degrees rotation of it. So if you think about it, then you can write down an expression for every coordinate of any number multiplied by z. Here we have a times z plus b times zi. And since we know what z and zi are and where they are, every number on the complex plane will be just scaled up by a and b, which means that in our example the vector of 1 is going to get multiplied, its length is going to get multiplied by the length of the vector of the z point, which is going to scale up 1, and it's going to scale up every other number by the length of z. So here we have w, and it's also going to be scaled up by the length of z. And it's going to get rotated around the origin And what's important here is that it's going to get rotated by the same angle, no matter what the point is. The rotation will be the same angle. So let's now use this fact to calculate some trigonometry.
Okay, so here we have unit circle, and our z is, as here is written, is cosine of alpha of f of a plus e times sinus a. And as we may notice, the one is rotated by alpha, by alpha angle, and it's important, and it's let us prove another interesting identifier.
Yeah, so if you remember, the multiplication by number z here rotates 1 by an angle alpha, but since we proved in the last example that the rotation is constant no matter what the number is, then every number rotated by multiplied by z is rotated by alpha. So now let's use this to our advantage. So we're going to calculate the cosine and sine of a sum of two angles. So here we have a point z representing the angle 75 degrees, and we don't know what its cosine and sine are, but we know what the cosine and sine of 45 and 30 are, and 75 is equal to 45 plus 30. So we're going to rotate 1, which we don't need to write, by 45 degrees around the circle. So here's the number for rotation of 45 degrees, and again by 30 degrees. So here we have the algebraic form, calculating all of this, and it turns out that the cosine of 75 is the square root of 6 minus the square root of 2 divided by 4, and the sine is the square root of 6 plus the square root of 2 divided by 4. So what we can do is generalize that rule.
Yeah, so if we have cosine of alpha plus beta, or sinus of alpha plus beta, it's we may turn it first by alpha angle and then by beta angle. So it is cosine of alpha and sine of alpha times cosine of beta plus sine of beta, and simplifying it, we may notice that cosine of alpha plus beta is cosine of alpha times cosine of beta minus sine of alpha times sinus of beta, and sinus of alpha plus beta equals to cosine of alpha times sine of beta plus cosine of beta times sine of alpha.
We can also prove an identity for the square of a cosine. So we're going to take an angle alpha and square its corresponding point on the unit circle. So we're going to take the point of rotation by alpha and then rotate it by alpha again. So we're going to get this expression, and if you may notice, we rotated by alpha and alpha again, which is 2 alpha. So we may write that the cosine of 2 alpha is this part here. It's the real part of the expression. So we have cosine of 2 alpha equal cosine squared alpha minus sine squared of alpha. And if you remember the identity in the first table of identities, we had that 1 was equal sine squared alpha plus cosine squared of alpha. So sine squared of alpha is just 1 minus cosine squared of alpha. So we substitute it, and we take out the parentheses. We have cosine of 2 alpha equal 2 cosine squared of alpha minus 1. So rearranging a bit, we have cosine squared of alpha equal cosine of 2 alpha plus 1 over 2.
Okay, so here we have another identifiers. The first three ones were proved were proved before, but we have also really interesting theorem, which is called the Mover's theorem, and it lets us count quite easily the big amounts of alpha, sinus of big amounts of alpha, and there is also one task in tasks, which we gave.
So here are some questions you might want to do, since they are related to the topics we talked about. They will definitely test if you understood everything. And if you want to do them, just pause the video now and make a photo of the questions. They are probably not that hard, but if you have any questions, you may write to us, text us, just ask us. Uh, so that would be the end of the presentation, and I hope you enjoyed and learned something today. Krzysiu, do you want to say something?
Okay, so thanks for hearing us.
Yeah, so see you in September, since schools don't work really.
See you.